Welcome back to the third installment of the AP Chemistry Chapter 8 Thermochemistry Problem Set. I'm Mr. Wilkosz. Let's take a look at question 35. In question 35, you're asked to calculate the change in enthalpy for the decomposition of 1 mole of C2H2 to its elements at 25 degrees Celsius and 1 atmosphere, and you're given the following equations. Equation 1. C2H2 plus 5 halves O2 gives you 2 CO2s plus H2O with a associated negative enthalpy change. Equation 2, carbon plus oxygen O2 gives you CO2 with associated negative enthalpy change. I'm calling it equation 2 delta H, or enthalpy change 2 with a little subgroup 2. Equation 3, H2 gas plus 1 half O2 gets you H2O, and the enthalpy change delta H3 is negative 285.8 kilojoules. The reaction we actually want is for the decomposition of 1 mole of C2H2 to its respective elements. So there's C2H2, we're decomposing it into 2C and H2. We want to know what the enthalpy change for that particular reaction is, and we can figure that out using the enthalpy change given for the first three ones. So you have to combine equations 1, 2, and 3 to yield equation 4. Equation 1 as it is, if you just recopy it, is useful to us. If we reverse and double equation 2, so therefore then reverse and double the enthalpy change, and I'm calling this delta H2 prime, and reverse means change the sign of it. And if we reverse equation 3, and therefore reverse the sign of the enthalpy change associated with equation 3, we can sum up the equations, and then we actually cancel out stuff. 5 half oxygen on one side cancels out with a half oxygen, and then the other oxygen, these 2 oxygen will also cancel out, and then H2O will cancel out with H2O, and then there's some CO2 that will cancel out, and when you sum them and simplify them up, you're left with C2H2 and 2 carbon and 2 H2. So if you sum up delta H1, which we didn't have to reverse or do anything to, and then delta H2 prime, which we had to reverse and double, and then delta H3 prime, which we just had to reverse, you'll get a total enthalpy change of negative 226.7 kilojoules. For question 39, you're given an equation where aluminum is decomposing to its elements and a heat enthalpy change associated with that equation. They want to know what the heat of formation at the standard temperature. So this naught up top means standard temperature and pressure. Heat of formation means we're going to make 1 mole of it. So we have to adjust the information that's given in this top equation such that we'll end up with forming 1 mole of Al2O3. So the equation is really making 1 mole of Al2O3 from its component elements. So we're going to have to change the direction of the equation. So instead of a positive value here, we're going to make it a negative value, and then we need to divide it by 2 because this equation that's given to us is considering 2 moles of the substance, and we only want 1. Part B of this particular equation says what would the standard enthalpy change for the formation of 12.50 grams, and now we're treating this again like a stoichiometric problem. Take your 12.50 grams, convert it into moles, and then use that value that we just discovered through part A to figure out the amount of enthalpy change associated with the reaction of 12.50 grams of aluminum oxide. For problem number 49, you're given information about chlorine trifluoride reacting, and a certain amount of heat is evolved. You can write a thermochemical equation. You got to go through and balance it, and they tell you that the heat is evolved, so you're going to have a negative delta H for this, a negative enthalpy change. They want to know what the heat of formation is for chlorine trifluoride. If you look at your table, it's not there, but table 8.3 will still help you with all the other stuff. If you use the equation that the enthalpy change of a given reaction is the sum of the heats of formations of the products minus the sum of the heats of formation of the reactants, you can actually treat this pretty much just like a problem where you're trying to find a single unknown. All the values for the heat of formation of nitrogen, heat of formation of chlorine, and 6 times the heat of formation of hydrogen fluoride, because there's a 6 as the coefficient, and the values for the heat of formation of ammonia are available from the table. So you substitute those in, and if it's a plain element, it's 0 anyway, so they just fall out, and then you solve out, and you can actually solve and divide and find this variable right here, delta HF naught of CLF